In a previous exercise, we've derived a formula to calculate the residue of a function which has a pole of order m. And it involved taking the function, multiplying it by z minus z naught, and then taking the limit at z naught. The question is, what do you need to do when your pole no longer has order 1, but order m? Well, this here is the answer. So pause the video and try and derive this result using a very similar procedure as we did when we were deriving the result for a pole of order 1. So in order to see more clearly what's going on, I'm not too fond of using the summation notation. So let's just try and write down explicitly what the Lorentz series of our function looks like. Since we know that we have a pole of order m, this means that the first term that will appear here in our Lorentz series is a minus m, having here z minus z naught to the power of m. And then we have lots of other terms until we arrive at a term which is of special interest to us, namely a minus 1, the residue, 1 over z minus z naught. And then we have a constant term, a 0, and then a 1, z minus z naught, and so on and so forth. Now the first thing we need to do, according to the recipe, is take our function f of z and multiply that by z minus z naught to the power of m. Okay, this gives us a minus m plus, and then some higher order terms, and then the relevant one, a minus 1, gives us z minus z naught to the power of m minus 1, and then we have a naught z minus z naught to the power of m plus a 1 z minus z naught to the power of m plus 1, and so on and so forth. Okay, so far so good. Next step in the recipe is taking the derivative of this function m minus 1 times. So all of these terms are very similar. They just have a coefficient and then a certain power of z minus z naught. So let's see how these behave when we take the derivative a certain number of times. So let's first focus our attention, for example, on taking the derivative once of a certain power of z. So let's say z minus z naught to the power of k. If we take the derivative once, then we get k z minus z naught to the power of k minus 1, right? Taking the derivative twice gives us k times k minus 1 z minus z naught to the power of k minus 2. Let's keep on repeating this until we take the derivative k times. So then we get a slightly different situation. So of course we all have these factors here. And then finally we get a factor k minus something. And then we have z minus z naught to a certain power, also k minus something. So what do we need to fill in here and here? So if we take the derivative once, we end up with k. If we take the derivative twice, we end up with k minus 1. So if we take the derivative k times, we end up with k minus 1 that we need to subtract. So we have k minus 1. So that's the pattern involving the prefactors here. Now let's look at the pattern involving the exponents. So there, if we take the derivative once, we have k minus 1. If we take the derivative twice, it's k minus 2. So if we take the derivative k times, it's k minus k. K minus k is, of course, 0. And if we then simplify this a little bit, it's basically k factorial, so a constant term that we end up with. Since this is a constant term, if we keep on taking derivatives here, so let's say we do the k plus 1 derivative, and also all of the other higher ones, they will all end up being equal to 0. So this is useful information to have when we now tackle taking the derivative of this whole beast up there. So what happens when we do that? So when we take the derivative k times, sorry, we need to take the derivative m minus 1 times in this case. So the m minus 1th derivative of our function f of z, z minus z naught to the power of m. What do we have? Well, first of all, let's take a look at all of the terms that, so let's scroll this down a little bit so that we can see what's going on. So if we take a look at all the terms before a minus 1, we're basically in this situation over here because we're taking the derivative more times than the highest order of z that we have in these terms over here. For example, the first term, if we take the derivative already once, it disappears, and so on and so forth. All these terms will disappear until we end up with this term here, a minus 1. Because this is a situation where we have a certain power of z, and we take a derivative also that same number of times as given by the power of z. So this is the situation that we had over here, where we take the derivative k times of z minus z naught to the power of k. So all of the first terms are 0 until we arrive at a term involving here k factorial. In our case, this will become m minus 1 factorial. So m minus 1 factorial times a1. Let's not forget the coefficient. a1, very crucial. That's the residue that we're interested in. And then for all of the higher order terms, so the ones up here, if we take the derivative, the important part is that we basically will have some factor z minus z naught left. So that's for a0, and then also a1 gives us z minus z naught squared, and so on and so forth. So the important part now is if we evaluate this whole expression in the point we're interested in z naught, then all of these guys over here will disappear, and the only thing we're left with is m minus 1 factorial times our residue. So this indeed shows that the recipe that we proposed to calculate the residue in that pole of order m is indeed valid.